Hi, this is Dr. B, and let's take a look at atomic orbital theory. In the very early 20th century, scientists such as Niels Bohr had a very simple model for the atom, a bunch of shells where electrons go from the outer shell and the inner shell. And it agreed with observed phenomena very well, but only for hydrogen. When they try to apply it to larger systems, which means like, I don't know, the other 117 elements or so, they ran into trouble, and eventually they had to modify the theory quite a bit. Scientists at the same time, or a little after Bohr, started looking at the model of the atom, not in terms of it being full of electrons that were particles of matter, but being full of electrons that really were more energy than anything else. Energy meaning light, if you will, and that means that they have a wavelength, that means they travel in waves, and that started to fit a little better. So the early model was just shells, nucleus with the first shell, second shell, third shell. Once it got applied to larger atoms, and this is primarily due to the work of Schrodinger and some other experimental data by Mikhailovsky to confirm these things, led to a model that looks more like this. First shell, fine, it's a sphere. Second shell, fine, it's a sphere, not just some spot where a hydrogen atom is like located, but anywhere within that spherical region, excluding the nucleus, or to put it another way, the probability of the electron being in the nucleus is 0. Don't forget that Thomson, before Bohr, suggested that that's exactly where it might be, but now we talk about the electron in terms of probability. It has an equal probability of being anywhere in that second shell, if that's the one we're talking about, but not in the nucleus, right? Now, there's also substructure to this. Maybe it's not so surprising that they found detail. Within the second shell, there's a region known as this, another region like this, another region like this. Going out to the third shell, fine, it has a wider radius, but there's also fine structure there as well. Okay, so that's atomic orbital theory. We call these subshells atomic orbitals. Think of them as pairs of electrons. We'll be dividing things up into 2-electron systems. Those are atomic orbitals. Okay, so fine, we have a shell. Each shell can hold a certain number of electrons total, but we also have subshells within them. We're going to divide it up into pairs of electrons. These are our subshells. We'll call them orbitals. And since it's gotten a little more complex, we'll have a little shorthand for expressing that. The level, that's the shell. The orbital, that's S, P, D, and F, the little letters we're going to use for the subshells. And the number of electrons in each will be expressed as an exponent. So bear with me. Here we go. The first shell, it can hold 2 electrons. The subshell within it is the only subshell within it for the first shell. We call it the s orbital, and it looks like that. So imagine for an atom, we have a nucleus and we have 2 electrons within that region, and we'll call that the 1s orbital. Therefore, the electron configuration is first shell, s subshell, 2 electrons, 1s2. We could also say that that is the electron configuration of helium, since that's a 2-electron system, right? Atomic number 2. We would say that the electron configuration of hydrogen is 1s1, so it would be in that orbital, but only 1 electron. Let's bring it out to the second shell. As you might have learned, it can hold 8 electrons total, but it's divided into pairs of electrons, and the first one is also called a s subshell. Perhaps you could think of it as standing for spherical. It is the 2s orbital, and therefore it's a little bigger, so still a sphere, and that's where the next 2 electrons go. Note that there's overlap with the first subshell, with the first shell, I should say, and so it's very different from Bohr's model. And therefore, the electron configuration for a 4-electron system would be 1s2, 2s2. Let's think about what we just said. The first 2 electrons, lower energy, go closer to the nucleus in a spherical region with equal probability. The next 2 electrons go in the next orbital, which is in the second shell, and that would be the electron configuration of boron. There is also 3 other subshells that have an unusual shape. That is the p sub x orbital, this is the 2p sub y orbital, and that orthogonal to it, which means perpendicular in 3 dimensions. Really, that should be just obscured the back lobe there, since it would be going in and out, if you will, is the 2p sub z orbital. We're now up to neon. This is 2p6. What have we said? The electron configuration for neon would have 2 electrons in the first shell, spherically oriented, 1s2. It would have 2 electrons in the second shell that are spherically oriented, but it would also have 6 additional electrons divided among these 3 atomic orbitals, which are the 2px, the 2py, and the 2pz. And that would be the electron configuration of neon, 1s2, 2s2, 2p6. Let's go out a little further. The third shell begins with the s orbital, and it can hold 2 electrons, and no surprise there, it's just a bigger sphere. So we're now at atomic number 12, I believe that's magnesium. It would be 1s2, 2s2, 2p6, 3s2, where all these numbers and letters are trying to give you an idea of exactly where the electrons are. We also have subshells for the third shell, and they are 3p sub x, 3p sub y, 3p sub z, just like the second shell, only with a larger radius. And that would be the electron configuration of, you should put a 3p6 right there, that would be the electron configuration of argon. I'm going to quickly explain where the electrons are in argon. There's 18 of them. 2 in the first shell, little sphere. 2 in the second shell, but in the s subshell, a bigger sphere. Another 6 in the second shell, but in the p group of subshells or orbitals. 2 electrons there, 2 electrons there, 2 electrons there. And we go out to the third shell, there's 2 electrons in a larger sphere, and 6 electrons in larger p-shaped orbitals, bringing us out to the end of that third shell there. That's 18 electrons. We're going to stop there. We'll find later that there is another pattern which is going to kick in as things get bigger, but it is a nice symmetrical pattern, and that's atomic orbital theory out to argon.